Hi everyone, welcome back to yet another video on our channel. Today we'll be talking about the topic of complex numbers, and for this topic we'll also be dividing it into two parts. The first part will be covering the base content, that you'll need to know all the new notation, symbols, everything to do with complex numbers. And in part 2, we will learn about the essential problem-solving strategies that you will need to tackle this topic and any questions that may arise. Alright, so what is a complex number? So remember when we were young and we learned that the squares of all numbers must be at least 0. So we never knew how to square root a negative number. And in the calculator, when we keyed in, like let's say square root of -1 or -3, all we get is a math error. So we never knew how to deal with this. So mathematicians actually came up with a solution to this problem, and they denote the square root of -1 as the imaginary number. And how we write it is just a letter I. Okay, so the square roots of all negative numbers are all in terms of I. So let's say we have the square root of -4. Then the square root of 4 itself is 2, right? So our answer would just be 2i, because this is equals to square root of 4 multiplied by square root of -1. This thing is I here, and this one is 2. So 2i. Okay, so remember when we were in secondary 1 and we learned about the hierarchy of numbers, rational numbers, integers, real numbers, all that. And there's actually a bigger umbrella of all numbers, including real numbers. So real numbers isn't like so-called the ultimate all-encompassing term to talk about all numbers. So we actually have complex numbers. So a complex number consists of two parts. It consists of both a real part and an imaginary part. So a complex number, let's say we call this complex number z, we write it as x plus yi. So this is the real part. Okay, we write this as re of the complex number z, and this here is the imaginary part because it contains our imaginary constant I. So this is the imaginary part of z. Alright, so how we represent a complex number in what we call an Argand diagram is almost exactly how we represent a set of Cartesian coordinates. So this is our regular Cartesian coordinates, right? We have a y-axis, x-axis. This is our origin, and we can have a point A, and the x here will be the x-coordinate, and the y here will be the y-coordinate. So for complex numbers, we actually have something really similar. So this is the Argand diagram, and instead of having y and x as our axes, we have the real part and the imaginary axis. So the real axis is the horizontal axis, and the imaginary axis is the vertical axis. So let's say we have a complex number z equals to x plus yi. Right, so x would be the real part. So we can just, this is our x over here. And for yi, it will be a height of y on the imaginary axis. So it is very similar to the Cartesian plane. Right, so complex numbers are actually vectors. So remember earlier in our vectors crash course, we talked about how vectors are basically a set of directions, instructions for directions to travel. So as you can see, each complex number actually represents a point on this Argand diagram, and it is a positional vector with respect to the origin. So we are traveling from the origin to this point. So the complex number is actually this vector over here. So just like all vectors, complex numbers can be located on an Argand diagram and also represented using its magnitude and direction. Okay, so the magnitude is simply the length r of the complex number vector, and the direction is the angle theta. Okay, so we represent the direction of a complex number with an angle. Okay, angle with respect to the positive real axis. So it's not over here, it's this axis over here. Right, so this is our angle, which defines our direction, and the length of our vector here would be the magnitude of a complex number. So how do we calculate the magnitude of a complex number? Well, it's just like how we calculate the magnitude of a vector. So let's say we have a vector xy, or just a 2D vector, okay, not 3D vector. Then the magnitude of this vector will simply be square root of x squared plus y squared, because Pythagoras theorem. So here we see that the run is actually x units and the rise is y units. So if we use Pythagoras theorem, the length of r is simply the square root of x squared and y squared. And keep in mind, our complex number z is equals to x plus yi. Okay, so since each point on the Argand diagram corresponds to a unique complex number that has a unique set of magnitudes and directions, so we can represent any complex number or distinguish between any two complex numbers using only their magnitude and direction. Okay, so next, we want to talk about another form of representing complex numbers called the polar form. So earlier, this form of representing it as x plus yi, we actually call this the rectangular form. Okay, so there are a few other ways we can represent complex numbers. So the first way is what we call the polar form. So if you realize, looking at the so-called angle over here that determines the direction, right? This is our x and this is our r. So cosine theta is actually equals to adjacent over hypotenuse, which is x over r. So we can write x as r cosine theta. And similarly, we can write y as r sine theta, because sine theta is equals to y divided by r. So we can convert the rectangular form x plus yi into this form over here, right, where r here is our magnitude, or sometimes we call it the modulus. Right, modulus, sorry, let's call it z over here. So it's the modulus of the complex number, or basically the magnitude. And we have this extra thing in here, cosine theta plus I sine theta. And how do we get this? All we do is substitute r cosine theta and r sine theta into our rectangular form. Then we'll get this polar form over here. Alright, so the angle theta here that determines the direction of this complex number vector is also properly known as the argument of the complex number. So here we are actually using z, so let me change this to z, okay? So we have modulus and argument. So a complex number has two parts. So here in our polar form, this would be the modulus of the complex number, and this would be our argument. And remember, our modulus is also equals to square root of x squared plus y squared, as stated over here. Alright, and there's another form, the exponential form. We can actually write r cosine theta plus I sine theta in this very elegant form over here. So we keep the modulus, and instead of writing cosine theta plus I sine theta, we can combine it into e to the power of I multiplied by theta. Okay, so the thing about this argument over here, right, is that it has to satisfy this exact range. Minus pi is less than theta, less than or equals to pi. Right, so minus pi, the vector might be somewhere over here, right? Or let's say minus 3/4 pi might be over here. And pi is just rotated this way, so it's like kind of anti-clockwise kind of thing. Right, so when we talk about the complex numbers in the proper way of talking about it, the r is always non-negative. Okay, so r is non-negative because we are looking at the modulus, or it's kind of like the square root, right? Because we're taking x squared plus y squared square rooted to find the length or the magnitude of this vector. So how can it be negative? So by right, r is always non-negative, and the argument is always between minus pi and pi. Right, so minus pi would just be rotating this way, and pi would just be rotating this way. And from minus pi to pi, we basically cover all the possible angles that a complex number vector can take, right? So what if the question gives you a complex number that looks like this? Right, our r is minus 3, and our argument is clearly outside the range of minus pi and pi. So is this question even correct in this scenario? Right, so actually the question is still correct, okay? They just mean to trick you, so do not be tricked. So you might think of the modulus as minus 2019 and the argument as 2020, because if we recall, the exponential form is r e I to the power of theta. So you might think the argument is 2020, or here our modulus is minus 3 and argument is 9 pi over 5. But this is completely wrong. Alright, so the next thing we want to talk about here is some special values pertaining to complex numbers. So I want to bring your attention to this fact we learned earlier. E to the power of I times theta equals to cosine theta plus I sine theta. So we learned this when we converted the the polar form to the exponential form. So what happens when we put in theta equals 0, let's say. So when theta equals 0, ei times 0 would simply be cosine 0 plus I sine 0. And cosine 0 is 1, and sine 0 is 0. So this is simply equals to 1. Or we can simply realize that this is basically e to the power of 0, which is 1. Next, what happens if we put in pi over 2? Right, so when we put in pi over 2, it becomes cosine pi over 2 plus I sine pi over 2. Now cosine pi over 2 is equals to 0, right? So this is 0. And the sine pi over 2 is equals to 1. So e to the power of I times pi over 2 is simply equals to I. And the last one, which is the most beautiful identity in mathematics, e to the power of I times pi. Right, now when we sub in pi into our theta over here, right, we get cosine pi plus I sine pi. And we know cosine pi is equals to minus 1 and sine pi is equals to 0. So e to the power of I pi simply equals to minus 1. And this is beautiful because it relates three seemingly unrelated constants, right? We have e, we have pi, and we have the square root of minus 1. And when we put it in this form, it magically becomes minus 1. So this is really beautiful, and this is an important identity you have to remember. So just remember this, and you'll be able to deduce everything from it. Right, so let's move on. So next we're going to learn about the operations with complex numbers. So the easiest way to add two complex numbers is simply to use their rectangular form. So we mean the x plus yi kind of form. So to add two complex numbers, both in their rectangular form, we simply add up the real and imaginary components separately. So the real component of a plus bi is a, and here is x. So we add up, this is x here. Sorry, there's a typo. So yeah, so we add up the two real parts and we get a plus x. And we add up the imaginary parts, we get b plus y times I. So this is how we add two complex numbers to get a new complex number. Right. So with subtraction is the exact same thing. Right. So how about multiplication? So how do we multiply two complex numbers? So first we think about how we multiply regular variables like this. So we use the distributive law and we get wx plus wy plus x squared plus xy. So it is actually the same thing for complex numbers, right? We look at this complex number over here, we just do it the exact same way. So we pair w and y first. Get wy. Next we pair w and zi. So we get wzi plus xy I plus xz times I squared. Now I squared is equals to minus 1 because I is equals to the square root of minus 1. That's how it's defined, right? So xi times zi is equals to xz times minus 1, which is minus xz. Okay? So what we can do is we can simply combine the real and imaginary parts. So the real part will be wy minus xz, and the imaginary part will be wz plus xy I. So that's it. Okay, so next, moving on, there's actually another way to multiply two complex numbers. So let's say we have them in our polar form. So we have a modulus and we have our argument. And to multiply these two complex numbers would then be very easy. So we just combine the two moduluses, r1, r2, and we simply add up the powers. So e to the power of I times theta 1 plus theta 2. Okay, so it's the same for division. So if we divide two complex numbers, our new complex number will have modulus r1 over r2, and argument will become theta 1 minus theta 2. Right? It's just simple indices law. So what does this actually tell us about the modulus and the argument of the product and the division of two complex numbers? Alright, so we actually have the following four properties over here. So when we multiply two complex numbers, right, the new complex number has a modulus equals to the product of the original moduluses of the two complex numbers. So we can see from here. The modulus of this complex number is R1. The modulus of this complex number is R2. When we multiply them together, the modulus of the new complex number is R1, R2. Therefore, we have these two properties over here. Same for division. Right, next for argument. The argument of the product of two complex numbers is actually equal to the sum of the arguments of each complex number. So why this is true is because we have our indices law, right? When we multiply two e to the power of things, the powers will add up. So our first complex number has argument theta 1. Our second complex number has argument theta 2. So our final complex number will have argument theta 1 plus theta 2, which is just the sum of the arguments of the first two complex numbers. So it's the same for division, except we change it to a minus sign. Note, a common mistake would be to put a multiplication sign here and a division sign here. But this is wrong. Okay, it's kind of like logarithms, where if this is a logarithm, you'll be adding up the individual logs as well. Okay, so there are some operations with complex numbers we've just learned. So let's say we want to power n the entire complex number. So to do that, r e to the power of I theta, let's say we power it to n. Then our modulus would be raised to the power of n as well. So r becomes r to the power of n. And ei to the power ei theta equals to e to the power of I times n theta. So a similar thing for the nth root of a complex number. So how does this actually show on the Argand diagram? So let's think about it, okay? So when r is equals to 1, then our new modulus is still 1 to the power of n, which is equals to 1. So if r is equals to 1, nothing would be changing, right? The only thing that changes is the argument. So let's say we are trying to find ei theta squared. Our new argument will be ei 2 theta. Our new argument will be 2 theta. So let's say our original theta was, let's say, somewhere over here. So let's say this was our original complex number. The new complex number will simply be this, but rotated another theta. So it might be like this, but the modulus, the magnitude of it will be exactly the same. Alright, so when you're raising it to the power of n, we're basically rotating it n times. You can kind of think of it that way. Okay, but what if r is not 1? So let's say r is 2. Okay, we're going to do this. So from our original modulus being 2, the new modulus will be 4, right? So instead of only changing the angle, the argument, we also have to double the length of this new complex number. Right, so that is how you operate complex numbers. So it's the same thing for the nth root. Right, so let's label this as the imaginary plane and this as the real plane. Alright, so we actually forgot two things. So how do we divide in the rectangular form? And how do we find the square root, for example, in the rectangular form? So for division, the question may be something like this. How do you calculate 2 plus 30i divided by 4 plus 5i? So we haven't actually learned how to do this, right? So all we have learned is how to multiply, how to add, how to subtract. But how do we divide? So in order to be able to divide, we have to bring in the idea of the conjugate. Right, so the conjugate is actually the same as the original complex number, just that instead of the addition sign in front of the I, the imaginary part, we flip it to a minus sign. So if our original number was equals to 1 plus 2i, the conjugate of z will be equals to 1 minus 2i. And how do we write the conjugate of z? We write it with an asterisk. Okay, so the z asterisk is equals to 1 minus 2i. So sometimes you might see people write it as z bar. Okay, this is also acceptable, but in the exam you should be writing the asterisk form. This can be accepted as the printed form. Okay, so z asterisk is equals to 1 minus 2i, and that is the conjugate, the complex conjugate of the original complex number. Right, so what we do is we are actually kind of like rationalizing the denominator. Right, remember when we had weird denominators like this, we will be taught to multiply it by 1 minus square root 2. Because this is because of the a squared minus b squared equals to a plus b times a minus b formula. Right, so we can do a similar thing with the denominator over here. Okay, we multiply by the conjugate c minus di, and the bottom will become c squared minus di squared. And what is I squared? I squared is minus 1, right? So the minus and the minus will cancel out, so we get c squared plus d squared. And then on top, we can do our usual multiplication, and we'll be able to find the complex number. Okay, so just like how we rationalize the denominator, we want to kind of realize the denominator by making it a real number. So the top will just become a nice complex number, right? So we can divide the coefficients of that by this real number, and we'll be able to get a nice complex number in the rectangular form. Okay, so there's some properties of the conjugate. So let's say we have x plus yi, then x minus yi, it'll be the same value on the real axis, but on the imaginary axis, y will become minus y. So it's flipped or reflected about the real axis, the real horizontal axis. Okay, so as I said earlier, they're reflections of each other in the real axis on the Argand diagram. So the length of the modulus of these two are still the same, obviously, because it's equals to square root of x squared plus y squared. So the modulus of z is equals to the modulus of its conjugate, but the argument would be equals to the negative of the conjugate, because here we have theta and here we have minus theta. Remember, we are starting from the horizontal axis and rotating in either this direction or this direction. If you rotate this direction, it's positive. If you rotate this direction, it's negative. Right, so if we add up the two complex numbers together, we get x plus yi plus x minus yi. We realize the imaginary parts actually cancel out, and we just get 2 times the real part of the complex number. And a similar thing when we subtract it, the x will cancel out and we'll get 2 copies of the imaginary part. Okay, and the last one here is z multiplied by its conjugate. So in order to do this, let's write it out like this: x plus yi times x minus yi. Earlier we learned that this is kind of like rationalizing. We get x squared minus yi squared, which is plus y squared, correct? And this is actually equals to this thing over here squared. So it's equals to the modulus of z squared. Okay, so here are some properties of the conjugate. So are you able to express the conjugate in the polar and exponential form? So how we can do this is, instead of, let's say our not usual z is equals to r e to the power of I theta, right? Then our conjugate has the exact same modulus, so it's still r, but the argument is now the negative of original, so just like this. Right, and that's it. And as for exponential form, we're just replacing. As for the polar form, it's just r times cosine minus theta plus I sine minus theta. Right, so that's it. Okay, so some extra properties of the conjugate you can remember. So you can pause to take this down, and I'll be moving on. So there are some other operations in the rectangular form we have to think about. So how would you calculate 2 plus 3i to the power of some really big number? So let's say 7. Okay, or what about the square root of a complex number? So the square root of 2 plus 3i. So how are we going to go about doing these things? Right, so do you remember this? The linear combination we talked about in our vectors crash course? So we can actually apply a very similar thing to complex numbers. Because complex numbers are just like vectors. Actually, they are vectors. So we can think of a plus bi as a units of a real number 1 and b units of I, where 1 and I are basically unit vectors in the positive, real, and imaginary directions on the Argand diagram. Right, so it's kind of like a linear combination where our vectors are the vectors representing 1 and the vectors representing I. Right, so if we think of it like this, okay, so a times the vector of 1 plus b times the vector of I equals to c times the vector of 1 plus d times the vector of I. if we think of it like this, then we can use what we learned in linear combination, right? And simply compare the coefficients of the real and imaginary parts. So our A is equals to C, and B is equals to D. Alright, so this allows us to compare real and imaginary parts. So, for example, if we have this over here, we can instantly compare the real parts to get 3 equals to 3x plus 2y, and 6 equals to xy. Alright, and this also allows us to tackle the problem of square rooting. Let's say we want to square root the number 5 plus 12i. Okay, so we simply let the square root of 5 plus 12i be another complex number with real part and imaginary part we don't know yet, so we just write it as a plus bi. Okay, here a and b must be real numbers. Okay, so we then square both sides, so 5 plus 12i equals to a plus bi squared equals to a squared minus b squared plus 2abi. This has a minus in front because we are squaring bi, right? And whenever you have an I inside a square, I squared is equals to minus 1. So it will basically flip the sign in front, so it becomes a minus. And next we can apply what we learned and compare the real and imaginary parts. So 5 will be equals to a squared minus b squared, and 12 equals to 2ab. So we simply solve. From the second equation, b equals 6 over a, and solving we get a squared plus 4 times a squared minus 9 equals 0. So since we define a to be real, a will be either 3 or minus 3 from the second bracket. Right, because a can't be real if this is equal to 0. So the corresponding value of b would be 2 or minus 2. We just had to substitute it into the second equation. And then when we sub it back into our a plus bi, it's either 3 plus 2i or minus 3 minus 2i. So that's how you find the square root of a complex number. Right, so most likely you will not be doing this method beyond the third power or say cube root, okay? So doing powers is actually much more simple in the exponential form. So let's say I ask you to do 5i plus 7 to the power of 7. This would be really, really difficult, right? Because, okay, a way we could do this is using binomial theorem. So we could simply write it as 7, 0, 5 to the power of 7, 7, 0, plus so on, so on, so on. So you know the drill. 5i, 6, 7, 1, plus 7, 7, 5i, 0, 7, 7. So this is our usual binomial way we can use to do this. Okay, then we have to simplify each term manually, and it's just a very, very laborious process. Okay, so doing powers is actually much simpler in the exponential form, because when we have an exponential form like this, we want a power n, right? So let's say we are given this complex number over here, z equals to this. We want to find z to the power of 7. We just have to take this entire thing to the power of 7, which is 2 to the power of 7, e to the power of I times 7 pi over 5. And this would be a lot easier to do than to write it out in the rectangular form. And then after this, we can even convert it to the rectangular form. So we first convert it back to polar, which is 128 times cosine 7 pi over 5 plus I sine 7 pi over 5. This is equals to 128 cosine 7 pi over 5 plus 128 sine 7 pi over 5 I. So this would be your real part and this is your imaginary part. So this is a lot easier than having to go through this process over here. Okay, so next we're going to talk about the polynomial. So now most of us are pretty comfortable with seeing quadratics or cubics as shown on the screen. So these are actually what we call polynomials in general. So we can have up to x to the power of n. Right, so there's an important rule. So this is a rule of thumb. The polynomial with the highest x power being n, right? So the polynomial here we have x to the power of n. This polynomial will always have exactly n roots. So a quadratic always has 2 roots, and a cubic will always have 3 roots. Okay, so in a quadratic, we know the quadratic formula, minus b plus minus this quadratic formula over here. So what happens when the discriminant is negative? There are no real roots, right? So Let's consider something like x squared plus x plus 5 equals 0. Just now earlier we said that in any equation, in any polynomial, right, the highest power is 2, so there should be 2 roots. But we know that the discriminant is 1 squared minus 4 times 1 times 5. This is less than 0. So there aren't actually any real roots. So where do the 2 roots come from? So these 2 roots are actually both complex roots. So if we were to solve x squared plus x plus 5, right? Write it over here, x squared plus x plus 5 equals to 0. X is equals to minus 1 plus minus square root of minus 19 over 2, which is minus half plus minus square root 19i. So if we realize, these 2 roots are both complex roots. And since we have 2 roots, so our theorem still holds, right? A polynomial will have exactly 2 roots. So these 2 roots don't have to be real, right? They can be complex also. So these 2 complex roots are also conjugates of each other. One of them is minus half plus this. The other one is minus half minus 19i, square root 19i. So these are actually conjugates. So we reach another theorem, right? This is called the complex conjugate theorem. So given a polynomial with its coefficients all being real coefficients, remember, the coefficients have to be real, okay? Every single one. If not, the complex conjugate theorem will not hold. So the complex conjugate theorem states that if a plus bi is a root, then a minus bi is a root. So let's say I tell you that 2 plus 3i is the root of some random polynomial with power 5 or power 6, whatever, some super huge polynomial. Instantly, you'll be able to deduce one of the other roots of this polynomial, which should be 2 minus 3i. So this helps when you're trying to find out all the roots because you can basically pair them up, so it isn't that difficult a process. Alright, so we've come to the end of the basic concept that you'll need to know for complex numbers. And in the next video, we'll be sharing with you the different problem-solving strategies and how you can apply what you've learned here, all the properties of conjugate, rationalizing the denominator, everything. So you'll be learning how to apply these in different types of problems and the kind of tricky questions they like to test in the A-level paper. Right, so stay tuned for part 2.